All right, so now let's actually look at some examples of simplifying radical expressions. I'm going to go through these exact same examples twice. I'll record one version where I'm going through and I'm changing them to rational exponents first, so giving them fraction exponents first and then simplifying from there. And then I'll go through these exact same examples again where I break them down by just simply thinking about it and pulling out groupings. So the first one I'll do is where I change them to rational exponents. There are 8 examples. I might have went a little bit overboard, so if at some point you feel like you've got it and you don't want to watch all 8, that's great. I do suggest that you definitely watch the first 4, though. Okay, so if I look at this first one, I have the square root of 12 x to the 5th y to the 11th z. So first thing I'm going to do is break it down so that I know 12 has a perfect square in it. It's 4 and 3, 4 times 3. I'm going to rewrite x to the 5th as x to the 5 over 2, y to the 11th as y to the 11 over 2, and z as z to the 1 over 2, because if an exponent isn't written, it's 1. And now I'm going to go ahead and simplify my square root of 4, because I know what that is, and change all my fractions to mixed numbers. So I get 2 square root of 3, 2 goes into 5, 2 whole times, with 1/2 remaining. So I get 5 halves is 2.5. 2 goes into 11, 5 whole times with 1/2 remaining. And z to the 1/2 can't be simplified, so I will leave it. Now I'm going to go ahead and say, well, 2 and the square root of 3 can't be simplified any further. X squared can't either. X to the 1/2, if I change it back into radical form, is the square root of x to the 1. Because the 1 remains as the exponent part, the denominator, the 2, dictates my root, and remember with square roots I do not have to write an index. Y to the 5th can't be simplified. If I change y to the 1/2 back to radical form, it does become the square root of y to the 1, and z to the 1/2 becomes the square root of z to the 1. Again, both of these examples, notice my numerator stays as my exponent. My denominator determines my root, and square roots, you do not have to write an index for them. My final step on this, I've done all the simplifying I can do. All I want to do for my final answer is collect any terms that are not under the radical and write them out front, giving me 2x squared y to the 5th, and collect any terms that are under a radical and put them all together underneath one radical. So these factors here, giving me the square root of 3. X to the 1 is just x, y to the 1 is just y, z to the 1 is just z as my final answer in simplified form. Okay. Looking at my next example, I'm going to go ahead and do the same thing. I'm going to try to draw a little line here so that hopefully we can keep these straight, and I will also switch pen colors. All right, so here we go. I'm simplifying the square root of 18, a to the 5th, b to the ac cubed. So square root of 18 I know has a perfect square of 9, because 9 times 2 is 18. Yes, I know I can say 3 times 6, but neither of those are perfect squares, so I don't want to use them. I get a to the 5 over 2. Again, if there's no index written in it, is a 2, it's a square. B to the 8 over 2, and c to the 3 over 2. Square root of 9 I know is just 3. Square root of 2 is some crazy decimal, so I leave it under a radical. Asking myself, how many times does 2 go into 5? Well, it goes in there 2 whole times, giving me a to the 2 with 1/2 left over. How many times does 2 go into 8? Well, that goes in there 4 whole times with nothing left over, so I get just b to the 4th. And how many times, looking at the c variable, does 2 go into 3? It goes in there 1 whole time with 1/2 left over. Now I'm going to go ahead and convert anything that has a fractional exponent back into its radical form. So I'm going to leave the 3, leave the square root of 2, leave the a to the 1/2. The 2 on the bottom tells me to take the square root. The exponent stays, so I get the square root of a to the 1. b to the 4th stays, c to the 1 stays, which I know is just c. c to the 1/2 becomes the square root of c to the 1. Now all I need to do is collect my like factors, so anything not under a radical goes up to the front, giving me 3a, b to the 4th, c. Anything under a radical goes back, stays under the radical, but it all collects under one radical, giving me the square root of 2. A to the 1 is just a, c to the 1 is just c, and that is my final answer. All right, looking at the next couple examples. So the next two, we switch from having square roots to having a cube root and a fourth root. It all works the same, but now instead of taking out perfect squares, I will take out perfect cubes or perfect fours. There is a list of perfect cubes and perfect fours on the Moodle account if you want to print those out if you're not real familiar with those, to use those to help you. Remember, you can always do some scratch work too and go ahead and write out what is 2 cubed, what is 3 cubed, what is 4 cubed, what is 5 cubed, and check to see if the numbers under your radical can be divided by those numbers. So on example 3, I have the cube root of 36, a cubed, b to the 8th, z to the 4th. So I'm going to start by breaking it down. So I think about 36. I know that 2 cubed is 8. I know that 3 cubed is 27. I know that 4 cubed is 64. And I see that 36 is not divisible by any of those three numbers, which tells me 36 doesn't have any perfect cubes in it, so I just leave it under the cubed root exactly as it was, how I was given. A becomes a to the 3 over 3. B becomes 8 over 3. Z becomes z to the 4 over 3. I'm just going to keep dropping that cube root of 36 down since I've already determined that can't be reduced. 3 over 3 reduces to be a to the 1. 8 over 3, 3 goes into 8 2 whole times with 2/3 left over. 3 goes into 4 1 whole time with 1/3 left over. So same thing as before, I'm going to take anything that has a now a fractional exponent, and I'm going to put those back in radical form. Doing that, cube root of 36 still. A to the 1 is just a, b squared is b squared. B to the 2 over 3, well, the denominator of 3 tells me to do a cube root. The square, the exponent stays, or the numerator stays as an exponent. Z to the 1 is just z. The denominator tells me to use a cube root. The exponent or the numerator stays as the exponent. And now just cleaning up, anything that's not under the radical I'll pull to the front. So a, b squared, z. Remember that this does not belong to the z, it's part of my root, so careful with that. And then anything that is under a radical I'll pull all under the same radical, giving me the cube root of 36 b squared z to the 1, which is just z. Looking at the fourth example, I am simplifying the fourth root of 28 x to the 5th y to the 7th z cubed. So doing that, first thing I'm going to do is I'm going to ask myself, is there any way I can break up 28? Well, I know that 2 to the 4th is 2 times 2 times 2 times 2 is 16. 3 to the 4th is 3 times 3 times 3 times 3 is 81. Since 28 can't be divided by either of those, I see once again, just like in the last example, that 28 cannot, or the fourth root of 28 cannot be simplified. So I leave that under a radical. I get x to the 5 over 4, y to the 7 over 4, z to the 3 over 4. Leaving the fourth root of 28, again, it cannot be simplified. I ask myself, how many times does 4 go into 5? It goes in there one whole time with 1/4 remaining. How many times does 4 go into 7? It goes in there one whole time with 3/4 remaining. Because 4 will not go into 3 at all, this is not an improper fractions like these were. This cannot be changed to a mixed number. I'm going to just leave it as z to the 3 over 4. Putting now anything that has a radical, or excuse me, a fractional exponent back under a radical, which would be these three here. I'm going to have the fourth root of 28, x to the 1, which is just x. This 4 tells me to do a fourth root of x to the 1. Y to the 1 is just y. Y to the 3/4, the 4 tells me to use a fourth root. The 3 stays on the y. Doing the same thing with the z, I have the 4th root of z cubed. It's hard to squeeze that in there. Pulling anything that doesn't have a radical out to the front, I get x, I get y. Putting anything under a root back, all under the same root, I get 28 under the 4th root, x to the 1, which is just x, y cubed, and z cubed as my final answer. So those are the first 4 examples. I would suggest if you're still not getting it, continue watching these next 4. If you think you've got it, try these next 4 or try the next 1 or the next 2 and see if you can get your results to match up with mine. Or just watch through them if you're still kind of confused. All right, then example 5, 6, 7, and 8. On example 5, again, I have a square root, so I'm going to go ahead and say, well, if I break 25, 25 is a perfect square. So I'm just going to, for the first step, leave it as a square root of 25. I don't want to break it up because in my next step I'm going to change it to 5. If you wanted to change it to 5 in the first step, go ahead. X to the 4 over 2, y to the 9 over 2, and z to the 2 over 2. Square root of 25 is just 5. 4 over 2 reduces to be x squared. I'm sorry, my 4 is really sloppy. I don't know if that helped or not. 2 goes into 9 4 whole times with 1/2 remaining. 2 over 2 reduces to just 1. Putting anything that still has an exponential or fractional exponent, I want to put that as a radical. So y to the 1/2 is just the square root of y. Z to the 1 is just z. So pulling out everything that does not have a radical to the front and everything that does have a radical under the same radical, I get my final answer. Looking at example 6, now I am taking a cube root, and I'm taking the cube root of 54 times a to the 5th times b to the 4th times c to the 7th. Again, remember you can always do a little bit of scratch work. I know that 2 cubed is 8 and 54 cannot be divided by 8. I know 3 cubed is 27 and 27 times 2 is 54. So I'll start by saying the cube root of 27 times the cube root of 2 times a to the 5 over 3 times b to the 4 over 3 times z to the 10 over 3. Well, the cube root of 27 is just 3. I do not know the cube root of 2. It does not have any other perfect cubes, so I leave it. 3 goes into 5 one whole time with 2/3 remaining. 3 goes into 4 one whole time with 1/3 remaining. 3 goes into 10 3 whole times with 1/3 remaining. If you are not good at changing to mixed numbers in your head, remember you can do that. Do what you need. Do that setup on the side somewhere. And if you're not sure how to do it, talk to me in class and I can show you how to do that. Changing anything that is now still having a fractional exponent back to radical form, I get 3 times the cube root of 2, a to the 1, which is just a. A to the 2/3 tells me to do the 3rd root of a squared. B to the 1 is b. B to the 1/3 tells me to take the cube root of b to the 1. Z cubed. Z to the 1/3 tells me to take the cube root of z to the 1. Collecting anything that is not under a radical out front, 3a, b, z cubed. And anything that is under a radical back under the same radical, the cube root, right? 2a squared, b1, which is just b, and z1, which is just z. And there is my final answer. And then looking at the final 2 examples, going through it much the same way. I'm going to go ahead and take example 7 and rewrite it as the cube root of, well, are there any perfect cubes in 16? I should back up a second. And I know that 2 cubed is 8, and 16 is divisible by 8, so I'm going to go ahead and say that I have the cube root of 8 times the cube root of 2 times x to the 7 over 3 times y to the 8 over 3 times z to the 3 over 3, giving me 2 times the cube root of 2. 3 goes into 7 twice with a remainder of 1/3. 8 over 3 is y to the 2 and 2/3. And z to the 3 over 3 is just z to the 1. taking anything that has a fractional exponent and putting it back under the radical, I get to cube root of 2, x squared. X to the 1/3, the 3 tells me use a 3 for my root, keep it as x to the 1. Y squared drops down. Y to the 2/3 tells me 3 is my root. The square belongs to the y, and z to the 1 is just z. Pulling out anything that does not have a radical, I get 2x squared, y squared z. And taking everything that is under a radical and putting it under that same radical, that same cube root, I get 2, x to the 1 is just x, and y squared for my final answer. And then finally, looking at the last example here, I'm going to break it down and say, well, does 32 have any perfect 4s? Well, 2 to the 4th I know is 16, and 32 is divisible by 16. 16 times 2 is 32. So I will rewrite this as the 4th root of 16 times the 4th root of 2, x to the 6 over 4, y to the 4 over 4, and z to the 11 over 4. Well, the 4th root of 16 is just 2. I have no idea what the 4th root of 2 is. I'm going to leave it. 4 goes into 6 one whole time,